Alright everybody, Mr. Carlson here, and in this video I want to cover gas stoichiometry. So far we've looked at the ideal gas law and how we solve for things like pressure, volume, temperature, the number of moles of a gas, things like that. Now what we're going to do is we're going to look at how can we use those gas laws and the things that we've talked about with pressure, volume, and temperature. How can we use those principles to help us with stoichiometric calculations? And remember, with stoichiometry, remember what we're talking about there is when we're going from, like, let's say we want to convert from, whoops, I got to get a different thing here. When we're converting from, like, let's say grams, if I want to convert from the grams of something into moles, or from moles of one product into the moles of another, and then maybe back into the grams of something else. So remember, it's those type of conversions that we're looking at when we're talking about stoichiometry. So really, it's a little bit different in the fact that we're dealing with gases specifically, and then pressures and temperatures and things, but it's really the same principles of those stoichiometric calculations that we've already been doing. Now, before we can do that, though, we have to talk about something that we'll see in a lot of problems when it comes to gases, and it's this thing that is STP. It'll say that in a lot of your homework problems and things. It'll say a gas that is at STP is what it'll say. STP, all that means is it means standard temperature and pressure. Standard temperature and pressure. You sometimes might see it in a problem or something like this. It'll say, like, for example, it'll say some hydrogen gas at standard conditions, maybe. It'll say standard conditions. Standard conditions. Or it'll just say STP, like this. Or it'll say standard temperature and pressure. All of these mean the same thing, just standard conditions. And what we mean by standard conditions here is essentially we mean that this gas, if it's at standard temperature and pressure, the temperature that that gas then is at is 0 degrees Celsius or 273 Kelvin. The pressure of that gas, if it's at standard conditions, the pressure of that gas at standard conditions is 1 atmosphere, or 760 millimeters of mercury, or whatever conversion that you need, or 14.7 psi, whatever that is. But remember, for our ideal gas law, we're going to be using it in atmospheres, though. So 1 atmosphere of pressure at 0 degrees Celsius or 273 degrees Kelvin. Those are standard temperature and pressure. And so if a problem says at standard temp and pressure, that means it's at 0 degrees Celsius or 273 degrees K and 1 atmosphere pressure. Now here's the thing, though. We're going to take this a step further. If we take these standard conditions here, okay, and let's say that we plug them into, so here's our ideal gas law here. PV is equal to nRT. So we've got pressure, volume. Remember, N is the amount of moles of a gas, the number of moles. R is just the ideal gas constant. That number never changes. And then temperature. Let's say that we, at standard conditions, we know the temperature and we know the pressure. And let's just assume 1 mole of gas, okay? And what we're going to do is we're going to solve for the volume of this. So we're going to rearrange this equation to solve for the volume here, which is going to end up being the number of moles times the gas constant times the temperature over our pressure, okay? Now, if we solve for the volume here, what we're going to get, so again, we're just for 1 mole of gas. So for 1 mole for N, R, remember, is 0.08206 is our gas constant, and then the temperature, so at standard conditions, is 273 K over the pressure. again, at standard conditions is 1 atmosphere, so over 1. If we crunch the numbers on that, we get a volume of 22.4. 22.4 liters is what we would get. Now here's the thing. So that would be for that 22.4 liters, that would be the volume for any ideal gas, any gas, whether we're talking about helium or argon or hydrogen or nitrogen, any gas that is at standard conditions will take up a volume of 22.4 liters. Now, that's for an ideal gas, right? So for ideal conditions, which technically are, we can say, not possible, but they're close enough to this 22.4 that we can assume that volume essentially. So this 22.4 liters here, so that's for 1 mole of gas at standard conditions. So this is called the, this is the molar volume of an ideal gas. And again, what that means is that if I have 1 mole of any gas, 1 mole of any gas at standard conditions, it has this volume. Now, here's the thing. Since that's for 1 mole of gas, right, what we can do is we can write that as 22.4 liters per mole. And you guessed it, here we have a conversion factor to go between volume and moles of an ideal gas at standard conditions. So again, this only works if you've got a gas that's at 273 Kelvin and 1 atmosphere of pressure. So at standard conditions, that's what this is. If it's not at standard conditions, then this doesn't hold true. But if I have something at standard conditions, that means I can assume that that gas has this molar volume no matter the gas that I'm dealing with. Okay, so let's look at an example then. Let's take a look at this example here. I have a sample of nitrogen gas has a volume of 1.75 liters at standard temperature and pressure. How many moles of N2 then are present? Okay, so again, for this you could actually use, the ideal gas law. So the ideal gas law, again, PV is equal to nRT. We could use this equation to solve for this because it's giving you a volume here, and it tells you its standard temperature and pressure, so you know what the temperature is, you know what the pressure is, you know what the volume is, and so you could solve for N, right? Just rearrange this equation to solve for N, which would be PV over RT. You could do that, plug those in, and that would be just fine, but we could also do this shortcut just by using this value right here as a conversion factor. So I could take this volume that I have, 1.75 liters of N2, and I can convert that because I know that for an ideal gas at standard temperature and pressure, that 1 mole of it is going to have this volume right here. So if I know that I've got 1.75 liters, well, I can just multiply it by this conversion factor to figure out or convert into how many moles of gas, nitrogen gas, that I have, right? Since this is at standard temperature and pressure. So I'm just going to plug this in. I'm going to put 22.4 liters on the bottom, liters of N2. So I can cancel those out, and 1 mole of N2 on the top. So when I take 1.75 divided by 22.4, that will tell me how many moles of N2 are in this volume of 1.75 liters at standard temperature and pressure. So I crunch the numbers on this, and we should get 7.81 times 10 to the negative 2 moles of N2. And so that's how we could solve that problem, just using this as a conversion factor, the molar volume of an ideal gas at standard temperature and pressure. Okay, let's do another example here where we have a chemical reaction taking place. Okay, where they give us a chemical equation. It says calculate the volume of CO2 at standard temperature and pressure produced from the decomposition of 152 grams of CaCO3 by the reaction. Oh, I should have had the reaction on here. The reaction is this, CaCO3, which is a solid, and that's going to decompose into two things, into calcium oxide, which is solid, and CO2 gas. CO2 gas. Okay, so this is our reaction here. They tell us that we have 152 grams of this CaCO3 here, and they want us to figure out what is the volume then. What's the volume of gas that I'm going to create from this decomposition reaction? If I'm starting with 152 grams of solid CaCO3, some calcium carbonate here, and when it decomposes, how much gas am I going to make? How much CO2 gas am I going to make? What's the volume specifically is what it's asking for here. And now notice again, it says standard temperature and pressure as well. So I know that it's going to be standard conditions for this CO2 gas. So I know what the temperature and the pressure is going to be for this. I just can now solve for the volume. So the first thing I'm going to have to do, just like any other stoichiometric problem, right? The first thing I should do, if I don't already know, is convert this into moles, right? Because I'm going to have to use my molar ratios here to do some conversion. So I'm first going to convert this CaCO3 into how many moles I have. So I'm going to do that over here, 152 grams of CaCO3. Converting that into moles using the molar mass. So for this, getting that from the periodic table, we've got for every mole of CaCO3, it's 100.09 grams of CaCO3. So for this, I have 1.52 moles of calcium carbonate. Okay, so that's how many moles of calcium carbonate I have. I have 1.52 moles. Now here's the thing. Let's go back and make sure that this reaction here is balanced the way that we have it, because in order to use our molar ratios here, I need to make sure that this is balanced. So let me take a look here. I've got one calcium on the left. I've got one on the right. I've got one carbon on the left and one on the right. And then I've got three oxygens on the left. I've got 1, 2, 3. So this is already balanced. I don't have to add any coefficients here in front. So this is already balanced. It's a 1 to 1 to 1 ratio for this, which makes it pretty simple. Because now that I've solved for this, 1.52 moles of CaCO3, that means I'm also going to have, since this is a 1 to 1 molar ratio, right? There's 1 mole of this for every 1 mole of this. That means I'm going to have the same amount of moles of CO2 gas. All right, so 1.52 moles of CaCO3 means I also have 1.52 moles of CO2 gas. And now what I want to do is, I'm not done. I've solved for how many moles of CO2 gas I'm going to have, but I want to figure out what's the volume going to be from this. So if again, all we have to do for this is we can use this right here as our conversion factor, 22.4 liters per mole. And so I'll come back down here. This is at standard temperature and pressure, so I can definitely use this. So I'm going to multiply this by, and again, I want things to cancel out correctly, so I want 1 mole here on the bottom, 1 mole of CO2 on the bottom over 22.4 liters of CO2. So 1.52 times 22.4 would give me a volume of 34.1 liters of CO2. And that's how you would solve for that one. Hopefully those examples make some sense for you.